Hello everyone and welcome back to Calculus, the series where we explore differentiation rules. First, I'd like to thank all the nice people that support this channel by liking and subscribing. It helps a lot for me to make more videos for you to enjoy. Today is the last video about rules of differentiation, and soon we'll start looking at applications, since many of you are probably already questioning why we're computing derivatives at all. Now, please recall that in the last video we explored the chain rule. And then we ended the video with a question. How do we differentiate these two functions? Let's begin with the left one. However, before calculating, today I would like to first state the definition of the product rule. It simply states if our function y is composed of the product of two other functions u and v, then y derivative is simply u prime times v plus u times v prime. This simply states we differentiate u and multiply it with the original v, and then we add the original u times v derivative. An alternative notation would be the following. This basically means that in order to find the derivative of y, or f of x, we need four things. We need u, we need v, u prime, and v prime. Now the funny thing here is u and v are actually always already given. All we need to find is u prime and v prime. So let's go ahead and take a look at our example. Here you can see that this is clearly a multiplication between two different functions. We can actually set x plus 1 to the power of 4 as our u, and then the cubic root of 2 minus 3x squared could just be our v. Here for v, I simply rewrote the cubic root into an exponent, 1/3. And now all we need to do is compute the derivative of u and then of v. For u, according to the power rule, the derivative would be 4 times x plus 1 to the power of 3. And then by the chain rule, multiplied by the derivative of the inside. Inside of the parentheses, we have x plus 1, and its derivative is just 1. So we can just not write it. For the v function, however, we have to first apply the power rule, and we get 1/3 times 2 minus 3x to the power of negative 2/3. And then we see inside the parentheses we have another function, 2 minus 3x squared, and its derivative is negative 6x. So by the chain rule, we have to multiply this entire thing by negative 6x. So now that we have all the four components, u, v, u prime, and v prime, according to the definition of the product rule, we can formulate the y derivative. It would be u prime 4 times x plus 1 to the power of 3 times the original of v, 2 minus 3x squared to the power of 1/3. And we add that by the original of u, x plus 1 to the power of 4, and we multiply it by v prime, 1/3, 2 minus 3x to the power of negative 2/3, and times negative 6x. And this here would be the correct expression for our y derivative. However, it is pretty long and requires simplification, but I will leave that to you. Next up, we still have another example that we need to differentiate. So let's get straight into that. Again, I'd like to start again with the definition before the example. Only this time, the definition is for the quotient rule. It basically says if our function y is in the form of u over v, then the y derivative would be u prime times v minus v prime times u, and all of this divided by v squared. In this case, again, u and v are just functions. An alternative notation would be the following. Once again, to compute this derivative of a complex fractional function, all we need are four things: u, v, v prime, and u. And just like before, u and v, two of these things are always already given in the question. So let's take our example and try to solve it. Here you can see that the numerator, negative 3x, we can simply set it as our u. And then in the denominator, the square root of 4 minus 3x squared, we can just set it as v. Once again, I rewrote the root into the power of 1 over 2, so that I can easily apply the power rule when I compute the derivative of v later on. So now if u is equal to negative 3x, then u derivative, or u prime, is just negative 3. And for v, well, first we apply the power rule. We get 1/2 times 4 minus 3x squared to the power of negative 1/2. And then applying the chain rule, since inside the parentheses we have a function 4 minus 3x squared, its derivative would simply be negative 6x. So now that we have all of the four components we need, we can find the expression for y prime. So firstly, u prime times v, negative 3 times original of v, 4 minus 3x squared to the power of 1/2. And we subtract this by v prime, 1/2, 4 minus 3x squared to the power of negative 1/2 times negative 6, and multiplied by the original of u, which is negative 3x. And we divide all of this by the square of the original v, which is 4 minus 3x squared to the power of 1/2, and we raise it to the power of 2. And conveniently for us, 1/2 and 2 cancel each other out, so we simply have 4 minus 3x squared left in the denominator. Again, this looks extremely complicated, so let's do a little simplification. This right here is what I got, and this would be your final answer. Some advice I can give you about the quotient rule, though, is that it is a very complicated formula, and I personally would avoid it whenever I can. As an example, with this function here, if I were asked to find the derivative of y, I would not use the quotient rule. Why? Because we can actually separate this fraction into three different ones. Once you have separated them, you can see that the fractions here and the x powers can cancel each other out and simplify. And with a simplified expression like this without any fractions, the derivative can be computed through the most basic power rules. All right, so now that we have finished all the most important differentiation rules, we can move on to the application of derivatives. To be precise, finding the tangent and normal of a curve in the next video. So I hope to see you there and have a nice day. Bye.